All right. This is a big lecture here, discussion on one of the most important theorems in 21B. We're going to use this theorem for the remainder of the course. We're going to be doing this all the time because what it basically does is gives us a way to evaluate a definite integral without doing a Riemann sum and doing the whole limit as we've been doing previously. So this is called the fundamental theorem of calculus. There's actually two parts to this. Part two is the most important part. That's the one that's going to really be useful for us, but we have to go through part one to get there. Okay, so we know now we're using an integral, a definite integral, could represent the area under a function, assuming the function was above the x-axis, of course. From t equals a to t equals x. And let's define that function to be y. It's a function of x. X is a variable, right? From some number a to some random number x. So there's lots of proofs, explanations for the fundamental theorem of calculus. Some are in the book. I know lots of professors like to prove this, and a lot of times I think it just gets really confusing. So this is the best way I've found to kind of understand what's happening. So I'm a runner, and so I'm going to use this as my context. Let's pretend that f of t, this function, represents the velocity of a runner at time t, the speed or the velocity of a runner. Now, what would the area, okay, let me move this down a little bit. What would then the area under a velocity function be? Well, we did some examples at the very beginning when we were estimating areas under curves. The area under a velocity curve gives you distance, okay? And you can imagine that if you just take one of those rectangles we've been using, the height of the rectangle would be measured in velocity, right? That would be the function value. That would be, let's say, meters per second. And the width of your rectangle would be measured in time, which is seconds. And when you find the area of that rectangle, you're going to multiply meters per second times seconds, which just gives you meters. So the area under this graph represents the total distance traveled by our runner, okay, from t equals a to t equals some number x. Okay, so then what would it mean to take the derivative if y represents that integral, which is the area under the curve, which represents the total distance traveled? What would it mean to take the derivative of this function? Well, we know from 21a, what is a synonymous phrase for derivative? The rate of change of something, right? So the derivative of y with respect to x would represent the rate of change of distance at t equals x, right? It's with respect to x, so that would be at t equals x. Well, if we agree with that, what is rate of change of distance traveled? Well, that's velocity, right? So dy dx would be the velocity of our runner at t equals x. And remember, f of t is a velocity curve. So if you wanted to know the velocity at t equals x, you would just plug in x into your velocity function. It would just be f of x. Okay. Now that hopefully makes sense and leads to this interesting result now. So what this is saying then is if you take the derivative of this definite integral, the integral from a to x of f of t dt, taking the derivative of that with respect to x, it's just going to be f of x. It's just going to be this function evaluated at your upper limit x. That's the fundamental theorem of calculus. Going back to the velocity distance explanation, that's fine. That's just saying that's the velocity, the rate of change of distance at t equals x is just going to be f of x, right? Also, we can tell that it doesn't depend on a, right? We want the rate of change at t equals x, not on my lower limit. We don't really care about that. Okay, so this is really big, important, and we do have to talk about part 2 of the fundamental theorem, but let's first get comfortable with some examples using part 1 of the fundamental theorem of calculus. So what this is saying, if I've got an integral, y is the integral from 4 to x of t squared dt, and I want to take the derivative of that integral, it's just going to be this function evaluated at x, which means I'm just going to replace that t with an x. It's just going to be x squared. It's that easy. Here's another one. Derivative with respect to x, the integral from 7 to x of t e to the t cubed dt. That would be my f of t, right? This right here is my f of t. Once again, I'm just plugging in x for this function, replacing my t's with x's. It really is that easy. Many times, not all the time. So we have to remember that the chain rule still applies. This is another derivative formula. This is kind of a continuation of 21a. And remember, when we learned a derivative formula for some kind of a function, with a chain rule applied, if we put more than just x into our function, right? For example, the derivative of sine of x is cosine of x, but if you put sine of x squared, it becomes cosine of x squared times 2x, right? The chain rule still applies. So this integral we're going to take the derivative of has more than just x, right? The fundamental theorem had only x there. This is more than just x. So what did the fundamental theorem say to do to take the derivative? We basically are just replacing our t with this x squared, which we do. But by the chain rule, we have to multiply by the derivative of the stuff. Let's see another one. Derivative of the integral square root of 1 plus t squared evaluated from 0 to ln of x. That's more than just x, so I'm going to just replace that in my function, square root of 1 plus ln of x squared, multiplied by the derivative of ln of x, which is 1 over x. What if the constant is in the upper limit? So like on my next example, I have the integral from e to the x to 5 of tangent of t. What do I do with that? Well, we know from earlier stuff that we learned that we can, if we want to reverse the order of integration, we're going to just put a negative out in front. And the fundamental theorem, this function of x does need to be in the top. It can't be in the bottom. So we're going to first reverse those limits of integration and put our negative there. And then to take the derivative of that, we're going to just replace the t with e to the x and multiply by the derivative of e to the x, which is e to the x, of course. Notice you're not multiplying by the derivative of the whole tangent. It's only the part that was more than just x that you substituted in, right? And then the last possibility is what if both of my limits are functions? Okay, let's look at this next example. So here I want to take the derivative of this integral, that's the integral from x squared to e to the x, 1 over 1 plus t cubed dt. The fundamental theorem tells us how to take the derivative of an integral from a constant to a function, okay? But not if both of these are functions. So what we're going to do is split this up, okay? We're going to argue as long as, okay, we're not thinking about an x value where these two functions are equal to each other. As long as that's not true, there's an infinite number of constants between these two limits. For example, if x is 2, this lower limit is 4, right? It's 2 squared, and my upper limit is e squared. there's an infinite number of constants between 4 and e squared. So we're going to split this up from x squared to some constant. We don't have to know what it is. And then add to that the constant to e to the x. We've done that before. Now, before I take the derivative, I need to get this function on the top. So I'm going to flip that, put a negative. This one's ready to go. And then when I take my derivative, the negative will stay there. This is more than just x, so we're going to substitute it in and then take the derivative of x squared. E to the x, same thing. We're going to plug that in and take the derivative of e to the x. This fundamental theorem, part 1, can show up in some different formats. This question says, if the integral from 0 to x of f of t dt equals the inverse tan of e to the 5x, find f of x. So your cue there is, how would I get this to be f of x if I took the derivative, right? Because we know if we took the derivative, we would just plug in x for the t. But if I take the derivative of the left side, I also have to take the derivative of the right side. So taking the derivative of the left side is just f of x, and using your knowledge of derivatives from 21a, we're going to get 1 over 1 plus e to the 5x squared times the derivative of just e to the 5x. And then I simplified it. So in the next video, we'll look at part 2, which is the real important part of the fundamental theorem of calculus.